But then, what we are really here for, this is our first speaker, Laura Hayes, and she actually looks at the sun, our closest star. And she herself is actually from the rainy Ireland and now moved to rainy Holland, so the fact that she's watching the sun is a rarity actually in her normal daily life. And then she also is, as I've been told, a bike enthusiast, owning 5 bikes in 3 different countries. So I'm sure that she's going to have a very interesting talk, explaining about the sun, and I think specifically about magnetic activity in the sun and solar flares and how that interacts with the near-Earth environment. But I think she can tell you a whole lot more about that than I could. So here's Laura. Give her an applause.
Hello everyone. So yes, I'm Laura, and I'm here today to talk about a bit about my research, which is looking at the sun and its activity. I realised on my cycle over here, this is the first in-person talk I've given since February 2020, so I apologise if I'm a bit rusty. I don't know what to do with my hands. I'm like, So yeah, so the sun. So it's our closest star, and I hope by the end of this talk you will see how interesting it is as an astronomical object, and something we need to really think about in terms of space weather and kind of living in a modern society orbiting an active star. So you might have seen this quick movie here. This is actually an observation of the sun, and all these leaps is looking in the atmosphere of the sun. And what I particularly focus on in my research is looking at oscillations and waves and all this different types of stuff. But let's start off with just looking at the sun. Oh no. And this is kind of a joke, I guess, that goes back to being Irish and being in the Netherlands. It's very hard to look at the sun in visible light a lot of the time. But let's try that again. This is an image of the sun taken in white light, so light that's visible, sensitive to our own eyesight. So if you had a telescope on a clear day like today, and you put a solar filter on it, so just a general telescope with a proper solar filter so you don't burn your eye, the sun might look something like this. It doesn't look super exciting. It's just a yellow ball in the sky, something we're all used to. The Earth for scale is up at the top there, so we can see the sun is very, very large. In fact, it's 99.98% of the mass in the whole solar system. And this is what we call the photosphere of the sun, or the surface of the sun. And in terms of temperature, it's around 5,000 degrees Celsius, so pretty hot as temperatures go. But we'll see in a minute that's actually not that hot when we look at the atmosphere of the sun. Now again, it's quite boring. You might see some features. So these are these dark regions. Does anybody know what these are? No? Yes, it's sunspots. I'm sure some of you were just a bit quiet. So what these are dark regions called sunspots. And what they are, you can't really see here, but even there are little other dots there, so you can't really see them on the screen. But what they are really strong regions of magnetic field on the sun. They're so strong, in fact, they inhibit convection, so it actually looks a little bit cooler. Now again, not that exciting when you're thinking from, why do you look at this every day and why do we want to observe it some more? The interesting part comes when we start to look into the atmosphere of the sun. So if we look at the sun at a different wavelength, so looking at a different energy range, so this is looking at extreme ultraviolet images, with an instrument called the Solar Dynamics Observatory, we can see that this image is taken at the exact same time as the previous one, but we can see there's a lot more structure going on. There's a lot kind of mottling, we see dark regions, importantly we see bright regions, and we see those bright regions over the sunspots. So in regions of really strong magnetic fields, you see really kind of hot plasma. So on this colour scale, the kind of white region there is really, really, really hot plasma. Another thing to note is that when you go away from the sun into the atmosphere of the sun, it starts to get hotter. So that's something a little bit strange, it's something we still don't understand. It's like walking away from a fire but it starts to get hotter. And that's something we still don't really understand in stellar physics today, is why the atmospheres of these stars are hotter than the surface of the sun. What is that energy transfer going on there? But again, if we move out a little bit further, well, this is called an active region, sorry. So this is a region over those sunspots, high magnetic field, high plasma, hot density. If we move out a little bit further into the corona of the sun, and we look at it another wavelength, this is looking at 131 angstrom on the Solar Dynamics Observatory, so almost looking at X-rays, we can see again we have a slightly different structure. Again, this image is taken at the same time, and we start to see even hotter plasma. So it starts to go to 5 million degrees. So going back from the surface of the sun being 5,000 degrees, you move outwards, it goes up to millions of degrees. This is known as the coronal heating problem, something we still, again, don't know about today. But just to kind of give you an idea of how dynamic the sun is, if we focus in on this active region, and we look in several different wavelengths, so the yellow, the orange, and the blue are looking at 3 different EUV wavelengths, and this one shows the magnetic field map on the bottom right-hand corner. But if we play this, we can see over a course of minutes of hours, the sun is always changing. And what we're actually observing here is a big, massive release of energy called a solar flare. And it's really, really bright. It's so bright that even in the green one, looking at the really, really hottest plasma, it actually saturates the detectors. So again, the takeaway here is that the sun is really dynamic in the atmosphere. It's highly magnetic, it's continuously moving, it's really, really hot. And this bottom right-hand corner here, this is the magnetic field structure. So the white is positive and the black is negative. So in these active regions, when you have kind of this really strong magnetic field and really complex magnetic field, you have more activity, more energy release, more things that are of interest. And why I guess they're of interest is this is again an observation looking at a very large eruption from the sun. So we can see in this bottom left-hand corner here, a huge massive eruption occurs. A massive eruption of plasma and gas and magnetic field away from the sun. And think back to the scale of the Earth in comparison to that. Now if we zoom out from this, and we take an observation with a coronagraph, which blocks out the light of the sun, we can see how vast these eruptions are into space. So these eruptions are absolutely massive and shed out all this gas and material, like mega tons of energy into space. So this is taken with the ESSA so-called LASCO instrument. So again, if you think about us here on Earth, we're orbiting an active star that's continuously spitting out stuff into space. Yeah?
This is real time?
Yes, well, this is real time. So this observation actually, is from 2012, but I'll show you an observation from last week in a minute to show you how active the sun is.
And then real time, the speed at which, not in seconds?
There's a time scale on this. So yeah, it would be in minutes, I guess, the eruption. In terms of on the sun, it can be minutes, and then obviously as you go out, it's hours. So in terms of, I guess, if you're thinking about how quickly that can get to Earth, it's around 2 days. So you're talking about thousands of kilometers a second. So it's pretty fast. And just in terms of these eruptions, we may have heard terms like solar flares or coronal mass ejections, and these together cause a solar eruptive event. So a solar flare portion of this eruption is the radiation. So it's radiation in terms of light. So this image here on the left-hand side is looking at EUV, so we see really, really brightness. You see brightness not only in the extreme ultraviolet, but you see it in radio waves, in microwaves, infrared, visible light, all the way up to X-rays and gamma rays. You see the sun brightening in all of these wavelengths over very short timescales. And accompanying this solar flare is usually the actual eruption part. So this is the thing that takes a few days to get here. This is the mass and the magnetic field. Now in terms of trying to predict these,
What's the CME?
sorry, coronal mass ejection. Sorry, thanks for pointing that out, yes. So we can see that coronal mass ejection is so energetic that all those speckles are actually energetic particles from the sun interacting with the detector on board. So these two things together is a solar eruptive event. And I guess the takeaway here is a solar flare, the brightening radiation, like we see it in 8 minutes, and the CME takes around 2 days to get here. And why this all happens is that the sun has a very complex magnetic field. It rotates differentially, meaning that the center of the sun rotates quicker than the poles of the sun, meaning that the magnetic field gets really, really twisted and complicated, and you can have these massive loops that occur, and you can also have these open magnetic field lines. And even when there's not an eruption, there's a continuous stream of the solar wind, so it's this charged particles emanating away from the sun continuously. And I guess why we care about this is that, again, as I mentioned, we're living with an active star. And we need to kind of think of the realities of that. Luckily on Earth, we have a nice magnetic field that protects us from the majority of these charged particles that come towards us. And one of the nice things we have about space weather and the sun having this activity is that it gives us the aurora, so the northern lights. And what this actually is that energetic particles that are coming away from the sun, interacting with our own magnetic field, and actually coming in through the poles, and then interacting with the atmosphere. So if you're up in I don't know, Iceland and you look up at the aurora, what you're actually seeing is a particle from the sun interacting with the atmosphere around 100 kilometers up. So that's kind of crazy when you think about it. An actual piece of the sun is only 100 kilometers ahead of you. And the green light essentially is just these charged particles interacting with oxygen. And you can also have these charged particles interacting with nitrogen, which is kind of a bluey colour. Now that's all well and good, but now we are a society completely dependent on the technological infrastructure that we've built. And all of this technological infrastructure is of course then impacted by highly energetic particles and all the things that occur in the sun that then impact our nearest environment and our magnetic field. So one thing is, if you're in space, you don't have the protection of the magnetic field. So if you're an astronaut, you don't want the charged particle coming in and giving you a high dose of radiation or interacting with your spacesuit, and can be very, very detrimental. So particularly when we're thinking about going to Mars, you're going to be in space and protected for 6 months. This is something we really need to consider. We need to be able to understand space weather and build protections around that. Similarly, as we kind of showed from that previous image, satellites can be detected, could be affected. They can get single set offsets on their detector boards, and they can also cause atmospheric drag. If you're on a polar flight during a large solar storm, you can have enough radiation as 2 chest x-rays. And then really what people really focus on is that these storms cause geomagnetic currents in the atmosphere, which in turn cause more energy to flow in our power grids, which can blow transformers. So we kind of want to have a better understanding of space weather and the solar flares and things like that to be able to build better predictions. And one recent example of this, maybe people have heard of this, is that SpaceX recently launched 49 Starlink satellites in February of this year, and they've lost 40 of them due to a geomagnetic storm. So they really didn't think about space weather properly when they launched these things. They should have talked to someone like, well, not me, but a space. We're waiting to hire a solar physicist to kind of figure this stuff out. But really, I know this is really important. I'm kind of joking about it, but as well as there's like weather forecasters, there are kind of space weather forecasts that occur all the time. But obviously, we don't hear about it. It doesn't bother us on a day-to-day basis. But these would give forecasts to the power grid companies, to people like SpaceX. Maybe they didn't listen that time. I don't know. But if you ever have a launch from anything going to space, you usually would check the space weather forecast to see how we're getting on. And this is, I guess, we also want to have real-time monitoring of the sun. We also want to understand the physics behind these eruptions. And we only want to understand them because it will help us to understand them, building better predictions. And one way we can kind of do this is by looking at the sun in lots of different wavelengths, lots of different instruments. And I'm going to talk just as I finish up, about exciting new opportunities in solar physics at the moment due to ESSA's Solar Orbiter launch. So it was launched in 2020, just before the pandemic. Bless you. And it's now currently taking observations of the sun, which is really exciting. And what is really exciting about it, it has 10 different instruments on board. And it has both instruments of remote sensing, meaning it's taking images, so it's remotely sensing something, and also in situ instruments, so it's actually probing, the temperature, the densities, and the energetic particles. And essentially it provides this whole new view of the sun. And what's even more interesting about it is that it has a really interesting orbit. So usually when things look at the sun, we're looking at them, from geosynchronous orbit. We're looking from the same perspective as Earth. But Solar Orbiter goes really in close to the sun, and it also goes out of the ecliptic plane. So here kind of shows a timescale. So in November of this year, it came really close to Earth again, and now it's swung by, and it's never going to come back. It's going to keep getting closer to Earth and going out of this orbit. And it's going to give us this view of the sun that we've never had before. And this will help us to understand better about these solar flares, understand the physics behind why they occur, and be able to kind of help us again build those better predictions and to build better space weather models. So this is just an overview of the instrument. If anybody's interested, ESSA has a really good media online presence, which has a lot of interesting facts about it. But just to show all the different instruments and some of the results. So we have images of the sun, we have spectra of the sun, we have magnetic field measurements of the sun, we can see X-rays, we can see the energetic particle distributions. So it really is a solar orbiter that's going to probe all the different elements that we're interested in studying solar physics. And to give you just some first results, I showed you massive flares, I showed you massive eruptions. But the sun goes through a cycle. It goes through a cycle being very, 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 very low in activity. And also, we only really look at the larger events. Maybe there are smaller and smaller events, so small that we can't even see them. And perhaps this is what is actually heating the atmosphere of the sun, kind of a distribution of really, really small energetic events occurring all the time that's transferring the energy to heat the atmosphere. And this is observations where, for the first time using this extreme ultraviolet imager on board Solar Orbiter, we've been able to see these tiny, tiny, tiny flares. So this is looking in 2 different wavelengths. And these things have been termed campfires. So if we start to look closer and closer and closer into the sun, it looks like these brightenings that are occurring continuously, which is really interesting. So we want to understand, are these smaller events the same as the very, very large ones? And what is the connection there? Maybe that will tell us more about what's going on. And this is even more interesting, that this is taken when Solar Orbiter wasn't that close to the Sun. But in November this year, Solar Orbiter is going to go to 0.3 AU, which is really close. So we're at 1 AU, it's going to go to 0.3 AU. It's going to be the closest image we've ever taken of the Sun, so we'll even have better resolution on this. And to go back to these large eruptions, this is an amazing image that was taken in February this year, so around 2 weeks ago. And just to give you a scale, so EUI, the Extreme Ultraviolet Imager in Solar Orbiter, is unique in that it has a massive field of view. So we can actually see that this eruption is almost the same size as the Sun itself. So this is the largest prominent eruption. This is what we call this kind of large-scale structure eruption that we've ever actually observed in extreme ultraviolet images. And here's a movie just to show you, again, how grand that is. Now just to also consider that we've taken this image and it's shooting off that way. So it doesn't really have a very strong geomagnetic effect, so it doesn't have a very strong effect on Earth. But imagine if that was coming towards us. These are the ones that we really want to consider. And just to finish up, I kind of briefly mentioned that the Sun goes through solar cycles. So it goes through periods of high magnetic activity and low magnetic activity. And this is due to the fact that the magnetic field it's more like a dipole, and it gets really, really complicated, and it goes back to a dipole. This happens roughly every 11 years. And we can monitor this based on looking at sunspots. So the more sunspots there are, the more active it is. And this plot down here on the left-hand side shows the solar cycle started 2008. So that was the last solar cycle 24. And we can see at the end of 2019, nothing really happened. Each of those dots is a large solar flare. You can see nothing really happened. But since the start of this year, we've seen the Sun really starting to ramp up again. There's a lot more activity going on. It's kind of exciting from a solar physicist point of view. Maybe not if you're launching satellites into space. And this top plot here shows the X-ray emission from the Sun. So we had the first X-class flare last year, which is very exciting. And this is an actual image from the Sun today. And I'll just finish with, it's funny when we write proposals, we say like, oh God, if a big flare ever occurred, it'd be really bad for society. But then when one happens, all the solar physicists are like, yeah, this is amazing. So it's funny. So I'll finish up there. I hope you are inspired that the Sun is really interesting. It's my favourite star. And it's good not only from a space weather perspective, but also from an astronomical point of view. It's essentially a lab in the sky. We have no other astronomical object that has so much data on it that we can actually look under a telescope. So I think it's pretty hot. And I'll finish there. Thanks.
All right, and then we can go to questions. And Laura, if you could please repeat the question so that everyone can hear it in the audience.
Consider the solar flare of February 15 have an impact on the storms that were last week? Or
Oh yeah, okay, so the question was, do you mean like the weather storms? Yeah, so that's a great question. So the question was, can the solar storms have an impact on, terrestrial weather? Could they cause storms here on Earth? And the answer is no, not that we know of. So these kind of like large solar activity in terms of solar flares don't seem to have a significant effect on climate, for example, or anything like that. But it's a really good question. Yeah?
Fascinating story, thank you very much. If you look at the solar flares, you see when they expand along the magnetic lines.
Mm-hmm.
So the magnetic is really one of the key elements of how the Sun works and how the solar flares work.
Yeah.
Do we already have a solid theory about how the magnetic fields are originating and why they are producing the flares?
Yeah, that's another great question, and it's really a topic that people are really still trying to get to the bottom of. So we have an idea of the magnetic field of the Sun is generated kind of in the convection zone, and this tangent line in between the convection zone. So you have kind of energetic charged particles that are continuously in motion because it's a plasma and ionized gas, it's not solid, and this generates a magnetic field. But due to the differential rotation, as I kind of mentioned, you have the fact that it's a hot plasma, the magnetic field gets trapped within the plasma. So you have the middle of the Sun moving faster to the top of the Sun, and essentially you get all these tangling up. And that's a very kind of layman's way of looking at it, but I think there's a huge field of stellar activity and stellar magnetic activity to get to the bottom of what is really generating this magnetic field. And in particular, like how do you get a very, very large event? There's a case back in 1859 called the Carrington event, which was the largest solar flare ever recorded on date. And I think if that happened now, that would have a dramatic impact on our technological infrastructure. So how was they got to the case where there was enough magnetic energy being able to build up to happen, and why does that not happen all the time, or why is that the case? And now I'm just rambling, but I think the answer is we still don't really fully understand it.
How do we know about this case of 1859?
Yeah, that's another great question. I actually had originally some slides in about that, but I just took them out to keep this short. So the question is, how did we know about this storm in 1859? And it was actually the first ever reported event of a solar flare. So Richard Carrington, this was called the Carrington event. He's a British astronomer, and he was drawing sunspots as they did daily for many, many years. And he actually observed a very, very bright thing that occurred in the sunspot, which is very rare to happen. If you think these things happen over minutes, and he just happened to be looking at the sun at the right time in this one active region. And he noted it to be like, this is a crazy big brightening I saw. Did anybody else see it? And there was another astronomer in the UK that also saw it. Now, this is very strange. And what they found was then, around 2 days later, there was a massive geomagnetic storm. So they saw the magnetometers on Earth started to go off the scale, essentially. And the only technologies that they had back then were telegraph wires. And they found the telegraph wires actually were working without power being going on. There was stories of them being sparked. So essentially, there was a story between the UK and Boston, and telegraph wires were talking to each other. Is your power on? Like, no. So essentially, the currents in the atmosphere were actually running through the wires. And similarly, there was aurora noted as far south as Cuba. So it's really retrospectively we've gone back and realised that was the first kind of observation in that sense of a very large event that happened. But yeah.
Why does the CME travel slower than the solar flare?
Yeah, so another great question. So the solar flare is just light, so it's just radiation. So it just travels at the speed of light. So that's going to take 8 minutes. But then the CME, the coronal mass ejection, is actual like plasma and gas, so that can't travel at the speed of light. So it travels a bit slower, about 1,000 kilometers an hour. Thanks very much.